Okay, friends, today is Saturday, 8:30 p.m. in Indian Standard Time, and we are at the 27th week of the Saturday Manufacturing, the talks. So this is a mega webinar series going on different aspects of manufacturing, and our eminent speakers are from the industry and also from the academia, from India and also from abroad. Today we are going to, listen on an interesting concept rather, the integrated design and development of materials, products and manufacturing process for accelerated product deployment. We all know that manufacturing is very much transdisciplinary and it has got different stages. We work in silos. So there is an imminent need of a platform, integrated platform, which will cover all the aspects like the design of materials, product design, the manufacturability, the life cycle analysis, so and so. So our speaker today is Dr. B.P. Gautam. So Dr. Gautam is the Chief Scientist at the TCS Research and heads the Research and Innovation Program on Integrated Computational Materials and Manufacturing Engineering and Development of TCS PMAP platform. Gautam's primary interests include application of modeling and simulation, both physics-based and the database, for engineering analysis with emphasis on materials engineering and manufacturing process. We work closely with various industries in troubleshooting, enhancing and optimizing manufacturing process with targets on quality, productivity, and energy. His current interests extend to utilization of state-of-the-art machine learning and knowledge engineering frameworks for materials and manufacturing systems and products. Gautam holds 8 granted patents. He has published one book as well, and over 75 papers in journals and conference proceedings covering areas of application of finite element analysis, computational fluid dynamics, data sciences, knowledge engineering, optimization, and robust design applied to materials, manufacturing, and product engineering. He has been on many international conference organizing committees and also reviewer for a number of journals. Gautam has obtained his BTech in Mechanical Engineering as well as PhD in Applied Mechanics from IIT Madras. Gautam has been with TCS Research since 1994. So you can understand that he is having a tremendous experience in developing the integrated platform covering all aspects, materials, as I mentioned, the product, design, manufacturability, and life cycle analysis. With this, I request Dr. Gautam to start his talk.
Okay, thank you, Professor Paul, and thank you for giving me this opportunity to talk to the audience over here in this prestigious seminar series, talk series. I would appreciate if somebody can give me the rights to share my, yes, I got that, right? It's disappeared, the share right.
Yeah. Has it come, Ananta?
Okay, now it has come back. Yes. Are you able to see my screen now?
Yes.
Okay,
it's very much clear.
That's right. That's great. Okay. Okay, it will go away. All right. Okay. Once again, I would like to thank the organizers for giving me this opportunity. It is a wonderful opportunity to talk to so many people. I'm also glad to see Farooq over here in the audience, with whom we collaborated a lot, and a lot of what I'm going to talk, you can also, it's something that we have done together. So for all practical purposes, we can sort of see Farooq also as my co-speaker, though he may not be speaking today. Also, I'm glad we are also interacting quite a bit with Professor Paul, I will touch with what we are doing along with IIT Kharagpur towards the end briefly, but that is not the main part of my topic. What I'm going to talk today is basically there are lots of big silos between, if you go to an industry, the silos between the materials department, manufacturing department, design department, and so on and so forth. But the silos are natural because all of them are having expertise in different areas. They do interact, but the interactions are very limited in certain ways. It has worked quite well because of whatever the reasons are, but the way the industry is changing at the kind of a pace at which it is changing, these silos are becoming a big impediment for faster product development and so on and so forth. That is one aspect of it. But very often, it is not about silos exist for other reasons, but also because of the enablement is a key issue. So the kind of a digital world in which we are living in is also enabling the breaking of silos in a great way. So I will talk about these aspects with some examples from our own experiences. I will not be going very deep into the technical aspects. If somebody is interested, we can always connect and discuss the deeper technical aspects, but I would keep it at a very broad level of my thought process and what we are doing in our organization. As can be seen, I am a part of TCS Research. We have a big research wing in Tata Consultancy Services. Probably the moment we say TCS, people think about IT and software. While that is the key aspect of TCS, we also do a lot of other aspects. What we always see is that IT exists at the intersection of some domain, whether it is, in this case, I'm talking about manufacturing industry. It could be to do with biological sciences and systems. It could be do with social systems and so on and so forth. So IT is always at an intersection, and as TCS, we do a lot of research in both these disciplines as well as the intersections of these disciplines of computer science and various domains. I will also close with my acknowledgement, showing my acknowledgement slides at the end. You will see what I mean by that. So I will start off with an interesting problem very recently we have come across from one of our customers. I think this is pictures I've taken from internet for purposes of illustration. But what the interesting point over here is that this particular thing, as you can sort of see, that this is an electrical car. It's a plug-in charging that is happening. So there is a particular company, the tier 1 company, which makes these systems over here, what we are seeing over here. The place where you put the charger in and the charging occurs. They faced certain field problems. There were cracks somewhere in this kind of a regions over here after some time, and certainly the customers are complaining. Why is that happening? That's an interesting problem. You know, it's a very peculiar. I think this is probably not, most of the audience are muted, so I wouldn't probably ask a question. I will ask a question and answer myself. Is that why is this happening? The very interesting thing that happens here is that when many aspects have been taken care of while designing and manufacturing this product, people really didn't anticipate that somebody would step on over here with their foot and try to reach onto the top of the roof of the vehicle to do some things. And whenever such things happen, this piece will crack, maybe after a couple of such attempts. Now you can sort of see how you have to imagine the consumer behavior all around to take care of while designing products. Now, this is the first problem, which is unanticipated. But when they looked at it, they felt that the design is still adequate to take a reasonable amount of additional load and it should not be breaking. When there are further investigations done, it was realized, okay, before talking about realizing what is this part made of, it is a plastic injection molded part with short fiber reinforcement. Pretty strong, and it should have probably withstood the kind of a abuse that it has gone through, though it is unintended abuse. But what was realized is while molding, because these short fibers, they do get distributed, there are weaker points at certain locations where the fibers are not sufficiently aligned to provide the strength, which was not thought of while designing. People made certain assumptions on the fiber distribution, but which is not what is actually happening when you are molding it. And many people who know molding will know that based on how you are injecting, what are your injection points, what your geometry is, the fiber distributions may become very uneven. So what it calls for is anticipating what are all the different kind of loads that will come in, design it. While designing it, don't design it as a simple aspect of it. When you're actually, if you have decided on this is the kind of a manufacturing process we want to take, what is that this manufacturing process is going to bring in or cause issues, all of this have to be thought through to make a good design. So I thought I will give with a very interesting though unusual example where people unexpectedly stepping on something and breaking. But if you really go to the manufacturing industry, what are the key things that everybody talks about? One is the time to market and the cost. These are the problems that existed all along, and these are particularly nothing new there. But what is happening even more challenging in these days is mass customization. People want varieties of variants that suits their tastes and needs of the products that are coming in. And then another major aspect is to take care of sustainability. It is no longer about recycling, but it's also about cradle to cradle. That is what is required. So besides these two aspects and the increasing competition, the mass customization and sustainability is introducing even greater challenges. So one has to look at the entire life cycle, all the way from raw materials where they are sourced to the intermediate material products, and how we design using these intermediate material products from component levels to systems level, how these are manufactured and how do they manifest as products, and how do you take care of their service, and how do you really look at the end of the life. All of this has to be kept in mind while making a lot of all the design decisions that we are making and the manufacturing decisions. When I say design, it is about product design, it is about manufacturing design, it is about service design. All of that have to come into picture. And the needless to say, the big buzzwords that are there, you keep hearing are the industry 4.0, engineering 4.0, materials 4.0. Well, these are very nice, catchy phrases used well and abused equally. Nevertheless, they convey a message that there is a large amount of industrial transformation that is occurring, and it is predominantly driven by the world of digital of various forms, and that is what is going to make these additional responsibilities that are coming on the manufacturing industries to happen. So what is the need of the hour is to look at the problem in an integrated fashion across materials, processes, products. Very often while designing the products, people take material as some kind of a catalog system and use those products. Of course, there will be a local manufacturing knowledge will be associated with it, but there is generally very little tight integration with manufacturing while taking process decisions, while taking product design. So this is something that has to be brought in, and that is what we feel, at least I believe, will bring in a significant paradigm shift in meeting the needs of the modern product engineering, whether it is a sustainability, whether it is lightweighting of an automobile, whether it is reducing the cost, all of these aspects. So what it requires for the needs, as we discussed, we require an accelerated product development. So right in the early stage, we have to consider many aspects, including manufacture and recycle. Needless to say, we have to reduce prototyping and experiments that are required to accelerate the product development, and huge amount of focus on sustainability and circularity is something that is also driving a lot of product innovations these days. That requires enhancing and working very closely with manufacturing processes in the product development. So we need to look at, we need to optimize the whole thing in an integrated fashion, integrated with processes. And when you're actually manufacturing, knowing exactly where we are going to use the products, we need to, if there are deviations, we need to take dynamic process decisions and learn all of that is coming from the plants to feed back into the design. Now the same further gets goes down to the service performance. It comes out of, because of we have connected products, a car with a chip is feeding actually data back into the OEM's data centers quite a bit these days from some of the modern cars. So we have connected products. So we do know how the product is performing in service, what is the kind of use it is going through, and so on. And also we do talk about integrated vehicle monitoring systems or product performance monitoring systems and so on. So they also feed a lot of data, and all of this can feed back into making our decisions back into product design or a manufacturing design in the next stage. And again, the two more buzzwords that are broadly used, digital thread and digital twin. These are, well, again, I use the word buzzwords, but it is a lot of reality. It may mean different things for different people, but actually they are driving the innovation that is happening to enhance our engineering decision making with science, data, and knowledge. So I will focus predominantly from a materials perspective in this talk. So what are the challenges with materials? Materials development takes a huge amount of time and their deployment. So if you take an aerospace material, the typical cycle is about 20 to 25 years. From the day you conceive a material to develop that material, produce it in a form that it is robust enough to be used in an aircraft, establishing their design allowables with which you can make a design of an aircraft and put it in, design it and test it out. It's a long cycle. And in automotive, typically, it is not uncommon to talk about anywhere between 8 to 10 years to introduce a material and start designing with it. So it's a huge amount of time. Why? That is because of the complexity of the materials, right? We are talking about all the way certain effects will be at a quantum level. Sometimes corrosion is impacted by the electronic behavior of the material underlying and so on. The material itself is going through a huge amount of cycle in which it is evolving all the way from raw materials to intermediate products to final products that are going into our, let's say, vehicles. If I will take vehicles as an example to drive most of my talk today. So what we need is discovery of materials with desired properties and recyclability. Now recyclability is becoming a big issue. That is something very, very important, and next generation materials, this will become a driver for driving the new materials. Scaling up of this processing from lab to bulk, very often materials fail because we can produce and show fantastic properties in a lab, but they can't be produced in bulk in their repeatable, consistent properties. Even if we have, how do we design with it? This is non-trivial problem. People often don't understand how complex is the actual industrial design problem when you're using a material, what kind of information you need. So we need to be able to do all these designs with a very, very detailed material knowledge, something that is expressible. Sometimes it is not easily expressible. So considering that, some of the aspects that have come out, okay, fine. So that's the concept of integrated computational materials engineering has taken root about around 2008. And one of the earliest reports that is published by National Academy of Sciences in the US, where the word ICME is coined, is to, what it says is to enable optimization of materials, manufacturing processes, and component design long before components are fabricated. Long before the components are fabricated, by integrating the computational processes involved in a holistic system. So if we sort of look at the history of, let's say, again, let me stick to automobile industry. When I was a student way back in late 90s, when I visited an automotive industry, still the FEM is a very fancy tool at that point of the time. And when I asked some of the design engineers, how do you design? They're still working with this thick book of marks and rows, formula and so on, and they're making those decisions. And when I talked about FEM, they laughed. I said, oh, it will just give colorful pictures. It is of no use. But today, if you go to an automotive industry, no design occurs without an FEM and CFD as a backdrop. And a similar kind of a revolution is occurring with materials. It is more complex, no doubt about it, but there is a huge amount of developments that are happening, and that is something that just leverages. And then there is another report that's published by TMS, and Farooq is an author, a co-author for this report. In this is about what it also talks about. It requires integration of personnel, that is engineers, designers, computational models, experiments, design and manufacturing process across the product life cycle for the purpose of accelerating, reducing the cost. So this is going to be my key theme. We have been working with this inspiration for quite some time, and I will give some examples on this. So what is, so just before I switch to what we do, within the same report, the second one that I talked about, what they envisage, this TMS has envisaged is about a tight integration of the materials modeling into the entire product life cycle development. So if somebody is looking for these aspects, I would certainly recommend this report. It's a very fantastic report with a very, very strong industry view. I would recommend somebody who is interested to read this report. So now, what is that we do in our team? So if you really look at the product life cycle all the way from gathering requirements, I talked about just in the opening example, right? We didn't even anticipate that somebody would be stepping on that to reach the top of the car on a plug-in charging system to the recycle portion of it. Across this, we look inwards from a very materials perspective to bring in material-aware design of products manufacturing process, broadly driven by the concepts of ICME. We also work on looking outwards from physics, data, and knowledge-based modeling for product design to operations reliability. Today, I will focus more on the materials and looking inwards aspect. To achieve this, we work in various areas of research: process modeling and simulation, multi-scale modeling of materials. We also look at various aspects of how do we do design. So generative design is another new concept that is coming up quite a bit, and it will, because of the computational methods, infrastructure going up, you can actually explore lots of options, and generative design gives a very strong view of this. Of course, you should look at systems engineering when you're looking outwards, or actually even materials can be seen as systems. The use of data sciences and machine learning, and something very unique we work on is how do we model knowledge? Broadly in the area of engineering, how do you really model knowledge and make it available to people at the right time in the right context? While we do all of this research, we also convert this into technologies. We are also developing a digital platform to enable all of these things in a seamless fashion in an industry. That is called TCS PreMap. We are also working closely with IIT Kharagpur in one of the projects, which I briefly will touch upon on my last 1.5 slide. So let's look at one problem without going a lot into the details. I will touch upon. This is to do with the tires. Tires of an automotive industry require certain wear characteristics as well as stiffness characteristics. Both of them are important. Wear characteristics are important because you don't want the tire to wear out in a short period of time. Stiffness is equally important because that's exactly what gives you the ride comfort and stability and so on and so forth. So the tires have to perform in various fashions in steady state, when you are braking, when you are cornering, and so on and so forth. So it all materials engineering in the end. How the rubber, its reinforcement, actually a tire will have, and also metallic reinforcements for radial tires and so on. It's a huge amount of materials that are out there, and making these right decisions along with their manufacturing processes are very important. Again, one key driver for tires is that as people may know that tires are extremely environment unfriendly once their life cycle is over. They don't degrade. If you burn, incinerate it, it causes other problems. So there's a huge amount of talk on green tires. So that is an area we did. So some of the areas of, you can look at different types of reinforcements, different kind of cross-linking. So it starts the actual properties of the viscoelastic properties of this tire depend on what is happening at a molecular level. So we do a lot of molecular dynamics based simulations to understand the tire behavior. Then we can decide upon what is the degree of cross-linking we need, what kind of a reinforcement at what level is going to give the right kind of a properties, what should be the interfaces between the reinforcement and the matrix of the rubber, and so on and so forth. Then once we have that, it's not sufficient because it should be processable. For example, tire, one of the various processes when you are manufacturing a tire is an extrusion. You would extrude a rubber tube which becomes a carcass of the tire, and so on and so forth. So that these things have to be done. So how does it really behave? So if something I make and it cannot be produced, it is not something that is useful, because the nuances of the processing will be something. And finally, that also is going to impact how the properties will be distributed in the material when the actual final product comes and real final behavior occurs over here. So this is an example of how we need to look at in an integrated fashion. So here we are using finite element based simulations. Here we are using a coarse grain molecular dynamics feeding into a CFD based simulation. Here we are doing analysis at uh, molecular level to look at the interactions between the polymers, the reinforcements, and so on and so forth. Similar example on which I will talk a little bit more in the next few slides, after a couple of more slides, is on again similar problem from metals perspective. It's a geared work, is something that we have done a few years ago. I will touch upon that. But now what we have seen over here is a lot of science over here. We are talking about deep molecular level science. Here we are talking about rheology. Here we are talking about the structural behavior and the wear. But not this, this is not going to be all the time sufficient. So we also look at a lot of assistance from AI. I will touch upon this again. Something like a fatigue, how much ever powerful simulation tools you have, because of the very nature that it is a statistically tail properties that will determine the fatigue properties, it's much more tougher job to scientifically predict. So here we merged science and AI over here. Or if I want to solve an inverse problem in a manufacturing process, it's very complex, because you can achieve the same end state through varieties of routes, and the problems are not naturally invertible by nature. So how do you invert it? How do you, the typical way is to put it in an optimization framework, but the complex problems of this nature don't work. So again, we use concepts like Bayesian nets and so on to more easily solve the inverse problems. Or explore. You want to explore it, but you don't want to run a huge amount of simulation. So you want to do your every new simulation intelligently. And how do you really do that? I have done 10 simulations. I want to do my 11th simulation intelligently after learning from my 10 simulations. How do you do that? And so on. That these are all the places where AI or machine learning helps. And one more aspect, this is again a common thing, is that if you are going into material science, people always talk about microstructure or a structure at various scales. And there's a huge amount of interpretation by experts out there. And when we go to industry, often this becomes a debate point. The section A blames on section B blames on section C. If you go to a steel industry, the rolling mill blame the casting section that, oh, you didn't give me good thing. The caster say, no, yours rolling is a problem. Or ultimately, the guy who's forming the sheet, which is their customer, will say the problem is at your end. Sometimes the problem could be at that end. And so this is where actually, whenever these problems come out, people get into deep microstructural analysis. And how do you interpret? This is extremely, it's more of an art than a science. So we are trying to use AI and ML to convert this art into a reasonable science to the extent that is possible by trying to figure it out, understandable metrics out of these kind of structures. So we looked at AI. Now I will talk about something a little different, right? Actually, we have a lot of knowledge. This knowledge is available in varieties of documents. We do refer, if you go to an industry also, they sit and look after a lot of their past reports, which will become their guidance and so on. And these are extremely rich sources of information. And there's a lot to learn. So another thing that we are looking at is that look at natural language processing and other forms of AI to actually glean information, curate information from varieties of sources of documentation to help us take decisions. Because somewhere something is there, and if I'm making a decision in an integrated fashion, I need to collect all that kind of information together. So for example, a very, very complex search. If I have a bunch of documents related to steel, I want those documents where the carbon concentration by weight is between 0.1 to 0.5, which has been subjected to a tempering process for over 20 minutes in some temperature range. I got elongation more than this. Very, very complex query, right? So we have worked on this kind of thing. So this, what happens is that these tools will also feed a lot of information at various stages of decision making to because there is already out there some knowledge out there. So get it right at the right time, in the right fashion, rather than somebody trying to remember from their hat that, oh, I read that paper someday. That's good, but not always it happens. So that's a kind of a stuff we are working on. And then the last is the decision aid. That's about providing information. But actually, if you want to do a formal decisions, you have to adopt a lot of decision aid techniques. For example, this is a work that we have done quite a bit with Farooq and Janet and Jitesh, is on the robust optimization using compromise decision support. So you can explore the design space. You can explore the design space with robustness. Very often, we don't need absolute optimal conditions, or rather, as Farooq says, no, optimization of a complex system is an oxymoron, because that's a reality, because we don't know so many things. So what we want is something that works, something very good, that is acceptable, but also I don't want something extremely sensitive. So for example, I have designed in such a way that, I'm subjecting in between to some heat treatment process, and I say that, okay, you have to do heat treatment at 950. In reality, I may end up having plus or minus 5 or in plus or minus 10 degrees variation in my process. And if I have to maintain within plus or minus 1 degree, no industrial process can do if you are doing a huge heat treatment in a large scale. So it has to be a robust process. So these are the kind of things, or fuzzy ranking selections. And again, I mentioned a lot of new concepts that are coming on generative design, though it is a little bit different problem, but still a design problem in which we are working. If you really look at oil wells, this is an oil well which is picking up oil from a subsea. Then multiple oil wells are connected to what is called manifolds, and these multiple manifolds are connected. Ultimately, it goes into a ship up there. Extremely complex system of systems. So we are working with an oil and gas company to really, how do you actually, what happens typically is that these experts sit together, will look at the bathymetry of the sea, they look at the contours of oil in the underground and all. They'll assume that some 10-15 possible designs and they evaluate, pick up one of them. But very often that becomes suboptimal. So we are actually using these generative design concepts to actually explore hundreds of possibilities and rank them in a way. And so that after exploration, you rank them and you give the top 10 to these experts, and then they can decide upon that, rather than they're just using their hat off the hat, looking at the data and making some decisions. So these are all very, very important things. Not just that, it will be important. Even if you are designing a new material, you have to explore a complete complex composition space, and the concepts of this nature we are using to apply there as well. So now I will so far I have given a very generic overview. So I will go a little bit deep dive into one specific problem. So this is about designing a gears. So gears are very important transmission parts. Probably electrification is reducing the need for gearboxes in automotive industry, but gearboxes are still very, very important in many other industries. The typical vision that was talked about, it's of course it's a little dated, but by the target is 2025, which is still 4 years away, is that they want to improve the power density in a vehicle by 25% every 5 years. That's a big ask, actually. So that's a kind of a strong thing that we are talking about. So the challenge problem one of our customers given us is that they have a particular gearbox which is used in trucks. They want to increase the capacity of the load, the ability of the truck, the engine torque. They want to mount a larger, more powerful engine which produces 30% torque, so that the vehicle can work under. It's a mining truck, it can work under more complex situations. But the challenge they have given is that I have a gearbox, the footprint is given, you can't touch it. That is number one. So that means you have practically very, very, very limited geometric freedom. The second thing they said is that don't tell me that you should use a ferrium grade steels. That's way too expensive. At the most, you can tweak my composition a little here and there so that I am well within my cost limits. So with that, we started working. So of course, a typical, how does a gear design works is that people do a preliminary design using certain, AGMA is one of the standards, but people do modify those AGMA standards, make some design. It's a part of the materials also are selected, and then a finite element analysis typically is done for more detailed analysis, and that's frozen. material is assumed to be having certain properties which comes out of some testing. So what we have done over here is that we integrated the manufacturing process in a gear of steel. The most important manufacturing process is the carburization quenching process, which is actually imparting the hardness to the surface of the gear in a desired fashion. But what it does also is that it also introduces a lot of stresses onto the surface. Sometimes beneficial, some situations are not beneficial, detrimental. So can you manipulate this in such a way and the material composition and the properties by playing with the process without going to very exotic alloys, probably minor modifications in the chemistry? Can I address this problem? Is how we looked at, and of course we were able to solve it. So in this whole structure, we in the early stages, I said, right, the generative design or concept exploration, we used the concepts of compressed distance support. That's where actually, as I mentioned, with work with and material selection. We, of course, this is very straightforward. What we sort of see on the right, the fatigue analysis, it's a very standard thing. But what is special over here is that we are actually feeding in information from point to point, element to element, material properties, or Gauss point to Gauss point material properties that are coming out of my manufacturing simulation. So I have very, very distributed material properties, not just that, but also because I'm simulating the manufacturing process, I know what kind of a martensite is forming, what kind of precipitates are forming. So I know the properties, and I also know the residual stresses. So you can manipulate in such a way that you have the most favorable residual stresses and the most critical conditions. And but the impact of that you can only do if you feed that into the fatigue analysis. So we have done all of this integration to be able to get better out of combining a geometric design plus manufacturing design plus an alloy design. Alloy design we didn't touch so much, but predominantly the manufacturing process cycle design to get the properties. But while doing this, these are the standard simulations, but here it's a multi-scale modeling that we have done. We needed to solve a lot of inverse problems, so we used machine learning. I will talk about them in the next couple of slides. And also a lot of ML also used, because not one single way we can solve this whole problem. So this is a science part of it. This is a multi-scale modeling. I'm not getting into the complete details of it. How the phase transformations will occur, what precipitate will forming at what kind of a temperature cycles, what will be the hardness that is coming out of it, all of that, and the residual stresses. We simulated. This is the science. But one big problem that came into picture is that my computational materials engineering is fairly good for me to give decent values of the yield stress, hardness, and so on and so forth. But it is not good to give me fatigue values, because it's a extreme value properties of the distribution of the microstructure it depends on. I will not get into those details, so it is not able to give. But the most important property required is fatigue. Of course, strength is equally important, hardness is equally important, because it's important from a wear and other properties wise. So this is where we resorted to an application of AI and ML. So we have some properties that are predicted. We have certain database of the past, the processing conditions, the composition to fatigue properties, the distribution. So we use the concept of transfer learning. We are able to we predicted fatigue properties from the hardness using kind of thumb rules, and then recorrected it with actual data using a concept called transfer learning. So we have a far better predictor for my fatigue value. So had this not been there, the fatigue values we can theoretically predict, computationally predict with existing state of the art is very limited. So the way machine learning helped us, and then that has fed into our fatigue analysis, the residual stresses, the properties that are computed directly, indirectly, and all of this led to my analysis. And then when we close this whole loop and optimize it or explore it towards better design, we get better design. So in this process of exploration, as I mentioned, we looked at various the compromise distance support based techniques to explore certain space. The inverse problems, especially in the manufacturing, solving the inverse problems are very complex, as I mentioned already. So we used Bayesian network kind of techniques to solve these inverse problems, and putting all of these, we were actually first able to show that you will be able to achieve a gear of the same capacity with a 25% less weight. Of course, now you translate that the same size gear having 30% more ability to take load. So this is another example from a wind industry. Wind blades. Again, the similar problems are very similar. Large wind blades, right? People are now looking at much larger wind blades, and these are all made of composites. So how you take your in composites decisions are inherently material and product design have to go together. But what is more complex here is that still we make a lot of assumptions on curing. And indeed, the degree of cure, because these are giant structures, have a large impact, and we end up giving a huge amount of margins of safety to avoid distortions, failures, and so on and so forth. So we introduced, once an aerodynamic design is done, material selection design to manufacturing, looking at damage becomes a function of the degree of cure, and so on, to solve and address this problem. Some more details are here. So we started modeling all the way from microstructure level, that is fiber matrix interfaces, to subsystems, how they distort, and what will be actually the impact of the curing cycles, what you are doing on the properties. And when you actually cure the whole blade, actually not every point sees the same kind of a thermal cycle. You can't control it at a point level. So how does it happen? And linked up all of this stuff, and it led to certain improvements. So I gave a very broad overview of a couple of examples of problems. Now, let me touch a little bit on what actually happens. If these are all fine, you can solve these problems. But if you want to industrialize it, it is not easy. You have to make things available for people in the industry to easily use these tools and techniques to solve their problems. And this is even bigger challenge than doing some research. I mean, I'm not saying discounting the research, but taking people, saying that people, hey, these kind of techniques work. If you just say it won't, you have to demonstrate them. Even if you demonstrate them, that is not, you have to make it easy for them to use, and so on. That is one part of it. Now, the kind of problems I talked about, you have seen varieties of stuff that are there. We are talking about materials simulations. So we are looking at microstructure evolution, phase evolution, sometimes precipitate evolution, that's in the material. So the kind of scales, and each of these things are different kinds of tools we use. Then we feed that into a kind of a finite element analysis or something of that nature to do a stress analysis of the part. And also there is a design. So there are varieties of tools that have to be used. So these tools, sometimes the information has to flow what we call vertical integration. So my microstructure to mesoscale to the properties of the materials, which are about scales problem, but the same material is going through 2-3 processes and actually in service. So this is a horizontal process, and you have to use varieties of tools to make things happen. So this is simulation integration and the scale integration. And then we have to do design using these two different aspects. So, but you have to enable the design integration. You have to enable the decisions, not just about simulate. I simulate and I have got something, I plotted some report and so on. Not the practice is that you have to actually end up using this to make design decisions. When I say design, it could be a process design, it could be a product design, all forms of design. But when we are dealing with it, the simulations and all of that, fantastic. They are aids, great aids that help us. But there's also a huge amount of knowledge, tacit knowledge. While that is reducing the need for it, but still there's a huge amount of tacit knowledge. There are so many unknowns that cannot be modeled in these techniques. So the knowledge integration that has to happen. And of course, all of these things are consumers and generators of data. So you need data integration. So unless all of these are facilitated in the industry, they are not going to take up all these techniques. Otherwise, it will end up being in very, very silos. And this is another aspect we are looking at in our team in TCS. So that is where we have built this platform called TCS platform. TCS Premap. I will not go a lot of details on this. It's a platform for digital transformation of engineering, operations, and decision making across product process lifecycle. So that's what we are talking about. So how do you enable that? You require certain semantic connectivity across various ways of expression. You should be able to link these tools. All those integrations I talked about should be very easily be done. So that is what is being facilitated. I'm just not getting into the details of this. So before I close, it's also a work that we are doing with IIT Kharagpur. This is related to friction stir welding. Professor Paul and his students, we are working very closely with my team and one more team of TCS, which is based out of Kolkata, looking at various aspects where we are using also both the simulations, and some of our colleagues are working with Professor Paul's students in bringing in metallurgical aspects into the modeling of friction stir welding. We are also using the platform that I talked about, the pre-map, to make it easy to generate knowledge and feed into real-time process monitoring along with another TCS tool called Teacup. So those are the two over here. So that is the kind of a work I just thought, I will touch upon this work before I close. And the way I don't want to get into a long sermon of summarizing, but the way I sort of see is that the future product development will integrate tightly materials manufacturing and process design in the entire life cycle of product development. The key idea is to reduce as much experimentation as possible and improve all the processes, because that's where the time goes, expenses goes, and indeed they are also not environmentally friendly. The more experiments you do, of course, competition also equally has the other issues. And in all of these, digital technologies are going to play a very, very important role, and they're key enablers. And then finally, I want to close my talk with an acknowledgement. But along with the acknowledgement, I want to also convey a message. The names that are in the red over here, this is a short list of the examples that I've taken. We work on many, many other areas. The list is much larger. But the names in the red are metallurgists, material scientists. The names in the blue are predominantly mechanical aerospace engineers. The names in the green are computer scientists. And the ones in the black are information technology experts. So it is this kind of an integration across various disciplines that will also make things happen. People have to interact. I am a mechanical engineer, I am a metallurgist, I am A, I am B. I don't think that is the way in which we should work any longer in this world. It has to be in a very integrated fashion. And we were able to do the kind of a diverse problems only because such a very, very diverse team is able to work together in unison. Today, some of my colleagues who are computer scientists can talk decent amount of material science. I'm a mechanical engineer. I do talk decent amount of material science and computer science as well, and so on. I think this is what actually finally makes the integration really possible and succeed. With this, I will close my talk. Thank you very much. Professor Park, over to you.
Yeah, Dr. Gautam, it's a, wonderful description of, the integrated approach in manufacturing through your last slide. I really like that one because today, if you want to develop some integrated concept, for the materials, process, and then product, and also the digital technologies, you have rightly pointed out that digital technologies are very much needed for this integrated approach and all. We are very much grateful that you have highlighted so many examples like the design of the tires, going to the molecular level design, and the design of the wind turbine blade, so and so. It's really, it's a wonderful the presentation. Let us see some of the questions in the chat box.
Right.
Yeah, Professor Shubir Majumdar, I can see only one question right now. Professor Shubir Majumdar has mentioned that by designing a more robust door, wouldn't you encourage the behavior? In airplanes, there are clear markings, no step at various places.
Yes. Right. No, that is absolutely correct. No step and so on. But in airplane is a very controlled thing. Actually, the passengers are not allowed to enter any of those restricted places. And even those markings that you see on no step on this is essentially for maintaining people who are trained, controlled people. But if you are talking about an automobile, you really can't control people's behavior. Very difficult. You can always say no step, but that doesn't prevent people from not stepping on it. You can do that. It may reduce the problem, but that is where exactly when you're actually there was an interesting problem I heard from one of our friends who works in a tractor company, which is a US-based tractor company. When they introduced the same tractor over here, they were using the composite cowlings on the rear wheels, and they started braking. Why they are breaking in India? Because people here in the West, it doesn't happen, but in India it happens that people, if you see somebody riding a tractor, people sit on the towing on top of the tire. That God that is sitting on top of the tire. So that's a kind of a behavior, and you can't probably stop it. So they had to actually change the design to make it work. Rather, you can't go and change the people's behavior overnight. That's a long-standing process that can be done, but that's fine. I mean, but I think as an industry, we people have to look at these problems and solve it in advance, or solve it in retrospect. And changing people's behavior is a long-term parallel thing that we have to do.
Yeah. So another question is from Professor Tapan Bakshi. Where do you use prototyping?
Sorry?
The question is,
Where do you use prototyping? See, I would put it this way. There is always the question of confidence level at which you can make a decision on prototyping something or not. Again, I will go with certain examples from automotive industry. If you really look at an automotive industry, if something like a BMW or a JLR versus certain other things, they do have a very clear what do I call sort of index. What percentage of your components you pass through your analysis? What components, percentage of components you pass only after sufficient prototype testing? And the general targets is that 80 to 90% of the components they want to pass through without prototype testing, because you don't have to every time test a brackets or this and that and all those things. And as you are gaining more and more confidence in your analysis methods, you would like to reduce prototype testing. So the prototype testings are at two places where absolute criticality related to safety and other aspects come into picture. You have to do prototype testing, or where you don't have enough simulation uh, uh, confidence in the simulation, you still have to do prototype testing. It is not a either or a situation, but we would like to reduce as much of prototyping testing as possible at testing. So if you look at an automotive industry, they will always typically be striving towards more and more simulation confidence, reduce the amount of prototyping, but it is probably never likely to be eliminated completely, because you have to do crash testing. Actually, you have to do crash testing by regulation. There is no other choice. But for a small piece of a mounting or a body in white and stuff like that, predominantly a lot of decisions are taken without doing really a prototype testing all the time.
I see some of the participants are the doctoral scholars working in this area itself. So I do expect some questions from them. And before, Professor C.S. Kumar has mentioned that really happy to see another set of examples for the use of integrated design using CTSP approach of Farooq and Janet. It revived my memories of the work done in collaboration with them. Glad that TCS found good industrial use cases of these approaches. Thanks God. So it's an appreciation. Professor Tapan Bakshi has mentioned that what background do you expect new engineering recruits to have? That's a very
okay. This is a question. What is something that cannot be done away with? Is understanding of the fundamentals. I will put. I will be very recently. I was working with one of your sister IITs, and they are planning to introduce a undergraduate course in computational sciences or something of that nature. The argument is that most of the industries are going to look for people who can do simulations, blah blah blah, all that stuff. That's fantastic. But actually, not only me, but also there are a bunch of industry experts who are in that call. All of us are very unanimous and saying that I can probably much more easily teach them how to do a finite element simulation or a CFD or even a materials modeling. But if they don't come with understanding of, let's say, strength of materials or phase transformations or whatever that is required at a core level, sitting in industry, we can't teach them. It will take enormous amount of time. So I think students have to be very strong on fundamentals. The only thing is that what I feel is that start introducing them these fundamentals along with the computational approaches in a very parallel fashion, so that they actually learn what it really means. So this is what we find often missing in the students, is that it's almost like, actually in my own team, we actually take some of the best students that are coming out of IITs, that's at bachelor's level or a master's level, but still we find that the core fundamentals are not strong enough, and we would rather see those strong fundamentals strong with exposure to the computational techniques. So we can also start introducing them to what I would say computational experimentation. So that actually gives them a lot of insights on both fundamentals as well as the computational techniques. That is my thought process, but there is no escape from knowing fundamentals. So I would not truly encourage, merely building people with skill sets, especially not in some of the premier institutions like an IIT.
Yeah, so there is an appreciation from Dr. Dev Gupta for bringing all the aspects together. And the question is that applying these techniques, including global optimization like gradient search, sinks development time by 2 to 3 times. How is it in India? I'm not very clear about that question. Can you see, Gautam?
I will try to. I'm just applying this technique shorten, including global machines development time by 2x. Okay, how much time it reduces? See, I would put it this way. There are 3 ways of looking at it. Optimization may or may not reduce the time very often. What happens if you're not doing an optimization? What people will do is that they will do heuristic optimization, right? They will imagine, let's say, 10 scenarios. They will evaluate those 10 scenarios and pick the best out of them. That is what they do. The optimization, what it does is that it actually allows you to automatically explore hundreds of scenarios. These techniques, I would call, the word optimization is a very loosely used word. It allows me to use and explore hundreds of scenarios. The likelihood of me actually ending up with a better solution increases for the same amount of time that I spend. I can still, of course, I can, without using an optimization technique or gradient search techniques, I can do more scenario explorations, or it may be I'm such a superhuman being that my first guess will be the best guess. These are all subjectivities. But optimization, what it allows you is that it allows you to actually, it in a way automatically explores various things and comes you and gives you, okay, try this one. This is the best one. And so the optimization, I would put it this way, is that in the same amount of given time, these techniques help you improve your design, come up with a better design, better decisions, rather than worrying about 2x, 3x in terms of time.
I think there are no more questions. A lot of appreciations, Dr. Gautam, for your wonderful talk. Yeah. Just the concern from my side is that when you talk about the integrated approach, the covering all the domains of the disciplines and all, how do you think that how much it is effective in real time? The applications. Like different types of the simulations are involved, so getting data from one simulation, putting it into the other platform and all. So how do you think that how much it is effective in real time?
Right. So again, there is no single answer to this, right? The answer is that it is going to be effective. The question is what kind of a simulations you want to do. If you are going to do a simulation which runs for days on an HPC, real-time decisions are not going to be useful. But this can actually, if you can do these simulations of varieties of what if scenarios, curate certain amount of knowledge from that and push it into a real-time scenario. This is something that we are doing at a very, very large scale. Actually, we are working with a refinery. You can imagine the refinery is such a massively complex system, right? And we are able to, there are various ways, how do I run this? Okay, fine. Many times, if you go to a typically refinery, you will see HAZOP documents. HAZOP documents will talk about varieties of possibilities that can occur. Many things don't happen in real life. It may happen one day, which will become disastrous, but most often it doesn't happen. So what we are able to actually, we were actually using a lot of simulation to create all these things. And how do I actually even predict and forecast and preempt it. So that's why simulation plays an important role. If it is expensive, it becomes a creator of a knowledge base. But you can also build either low level simulations, very fairly simple mass balance, also a kind of a simulation. These things can happen very quickly, or you can build AI ML kind of a models, right, which are built on top of the simulations, which can be really applied in real time towards problem solving.
Yeah. I fully agree that the IML has got a big role in the simulation.
Right.
Yeah, so a lot of appreciations are coming up, Dr. Gautam from CS Kumar, from Professor Kapul Bakshi, everybody. And it's glad to see that there are a lot of people from the different parts of the globe are attending. There is one question from Dev. Dev Gupta is that in the US, these combines empirical and mathematical techniques have shrunk development times 2 to 3 times. Are they now being used in India, and what is the saving in development time?
Okay. Okay. See, saving in development time is always varies from situation to situation. I would put it, and I would be very honest with you is that we are a global company. We work with global customers, so we work across the world, and there is a lot of transformation occurring in India also, right? So using these techniques, if you look at a lot of product life cycle development times have shrunk at least by 50% in many situations because of this kind of a techniques. Many situations it have gone even further down then, because this 50%, because there are also many other aspects. So if you look at overall product life cycle development, at least in most many situations they have at least halved, in spite of many other things that are required. So the simulation and the around portion, my guess would be roughly it would have made it 3 to 4 times faster, because you really don't have to do if in a car, if you are avoiding prototyping for 80% of your components. I mean, let's say even in the traditional design method, you might not have done still 50% of the components prototyping, but at least if you eliminated 20% of the components prototyping, that's a huge amount of saving. I will put it in that sense. So, and the typical cycles have shrunk by about more than half.
Thank you. I think there is no more questions in the chat box. We have also reached to the scheduled time and all. So for Dr. Gautam, I must say that's a wonderful, the talk. We all have enjoyed. So thank you so much for, being present over here and then deliver this wonderful talk.
Thank you, Professor Paul. It's my pleasure to be on this August forum and share my thoughts with all our colleagues and students. Thank you very much.
I'm pretty sure the doctoral students who have attended, they will learn a lot out of your talk.
And if any of them want to have
Yes,
a little bit more chat and details, I'm always available for students.
In fact, that's one of the purposes of this, the conducting this sort of, the webinar.
Right.
Yeah. So I request Ananta to let us know the speakers for the next weeks. Oh, the next week, our speaker is Dr. Preet Banerjee. Dr. Preet Banerjee is the CTO and CIS. So he'll be talking about the digital twin. And then the last week on the September, Professor T. Kesavdas of University of Vanasampan. So Professor Kesavdas will be talking about the decision and control systems. So with this, So and then as usual in the month of October also the webinars are scheduled. All past webinars are we are doing the recording, and those recordings are also there in the Google Drive. The links are also getting shared through the email as well. So if any one of you miss any lecture, you can just scan this and to get to see the past webinars. Thank you so much. Thank you everybody for all your presence, and I'd like to see you again the next Saturday at 8:30 p.m. Indian Standard Time. Thank you so much.
Thank you.
Thank you. Bye.